Hi everyone, welcome to our ECRES 2020 conference. I'm Zheng-Yun from National Kaohsiung University of Science and Technology, and today I would like to talk to you about how the local regression method, LRM, can be used for preprocessing the vibration data of wind turbines. As a background, we know that there are mainly four types of wind turbines. There are shore-side wind turbines. When you drive along the coast, you see them. And there are inland wind turbines. For example, several such farms are near the Sahara Desert, for example, in Algeria. And there are fixed offshore wind turbines. For example, a large project is to be launched on the sea area of Taiwan Bank, where the water depth is only 4 meters in average. And there are also floating offshore wind turbines. There are many leading projects in Mediterranean countries. For example, in Italy, Libya, and others, to the author's knowledge. So, to preprocess the vibration data of wind turbines, we have four parts to talk about it. The first part is about the maintenance problem that drives this research. The second part is about how this study is progressed. And the third part shows the results. And the last part gives the conclusion. For the problem and necessity of this study, we know that typhoon is perhaps the killer for the turbine. And so, a mechanism is required to support the maintenance jobs. In some countries, natural disasters often bring serious challenges. For example, earthquake, tsunami, and typhoon. We know that typhoon is a type of natural disaster which mainly brings the problem to the wind-driven turbine component of the wind turbine. So a typhoon is perhaps the most harmful to the blades. When there is a typhoon, the wind becomes unstable and very strong. For example, a strong typhoon can easily bring us a wind speed about over 115 kilometers per hour, which is far surpassing the normal operational speed of any normal wind turbine. And more seriously, the direction of wind is always changing and unstable when the typhoon is striking. So what's our policy to face up with this? So this brings challenges to the designers, installers, and operators of the wind farm. And we know that when we are going to ensure the health of the turbine blades, there are preventive maintenance and event-driven maintenance. For the preventive maintenance jobs are usually those routine jobs. So these are out of the scope of the study. And for the event-driven maintenance jobs, we must see what type of disaster it is. If it is an earthquake, it is totally unpredictable. Okay. And if it is a tsunami, then it is just partly predictable. And this tells us that we have no way to do, almost no way to do with earthquake and tsunami. Compared to these unpredictable disasters, typhoon is predictable, but the wind of a typhoon is usually unstable and very high speed in the average, and the wind direction is very abnormal or changing. So these lead to unpredictable forces imposed on the wind-driven turbine set, which is serious for the blades. And even there are several special designs. For example, the mechanical retraction function of the brace or the yaw control system. This seems irresistible to the wind of typhoons. So the ultimate solution should be we have a self-working accelerometer sensor mounted on the platform of the wind turbine, and we record real-time data, and then we analyze the data periodically to know the status of the brace health accurately. So we can perform event-driven maintenance while required. This facilitates the operations. Then let's go on to introduce the concept of this study and the methods used in this study. Let's review the flow of typical big data analysis work. And the first step of a big data analysis involves the collection of data. So for our case, is to collect the data using the sensors and warehousing the data. And the second step is data preprocessing. So for us, we are to find the feature or pattern of a data set for subsequent data works. And normally, phase 3 is analysis. We can use, for example, the statistical methods or some other method to analyze the data. And the fourth step is prediction. Prediction, sometimes we have machine learning based predictions, and sometimes we have something like time series analysis predictions. So anyhow, we are to predict something. And the fifth step is decision making. Decision making involves we can provide automatic decision support functions, and we can provide these functions for the decision makers to act while required. For example, for our case, it is those repairing works. Okay. And what we do in this study is the red box. The red box shows the focus of this study, which is from phase 1 to phase 2. So if we do these phases well, phase 3 and phase 4 can be launched in the future on a solid basis, which is our next study. Except for the concept of this study, we introduce the methods. In this study, at first, the datasets are collected from a university lab near an onshore wind farm in Penghu, or the Pescadores. These contain the source data sequences that were recorded by the accelerometers under some different conditions. The accelerometers were installed for turbines with 3 malfunction situations on the brace, namely full brace or free blade, a half blade broken or 2.5 blade, and a full blade broken or 2 blade. For these 3 levels of severity, because we sampled the vibration data at 4 wind speeds, namely no wind, 10 meters per second, 20 meters per second, and 30 meters per second. And there are data for 3 axes, namely X, Y, and Z axes. We have a total number of 36 data sets. So actually, we have 3 data dimensions, and by treating these acceleration data sequences as data signals, many methods can be applied to process these digital signals, such as the local regression method, or LRM, in order to make the data smooth as a waveform which is easy to observe the patterns or features in this waveform, so that we can compare across the different data sets using these patterns and find some clues, for example, for the different malfunctional levels of the brace. Then, let's see the results obtained at this stage. including the data plots for the original vibration signals, and those plots for the waveforms using LRM. This page summarizes the source data plots for the normal case, in which no blade is out of order, and when there are only 2.5 blades, which means 1/2 of a blade on the turbine set is missing. The situations on each axis subject to each wind speed will differ a lot. We can compare this situation with the previous situations while no blade is broken. And when it comes to the source acceleration signals for the cases where a full blade of the blade is missing, which means the case of 2.0 blades. Here are the situations. Then we find that using the local regression methods for the first 1024 entries of data in each dataset, we can see the smooth line to represent the trend of the data points. Each smooth line is plotted as a bold blue line in the three sets of figures. In terms of a series of piecewise linear line segments using the method like connect the dots. This set of figures is for the 3.0 blade cases, and the other set of figures is for the 2.5 blade cases. And yet another set of figures is plotted for the 2.0 blade cases. So we can make some observations here. Firstly, in most of the figures, there is a waveform that contains several repeated waves with a quite static time cycle. And the time cycle of a waveform can roughly concur with the intervals between two nearby peaks or between two nearby valleys in the original signal. This means that perhaps the rules to distinguish the different malfunctional cases of blades can be established on this basis. Other features in these figures also provide clues to differentiate the different cases. For example, the amount of data points outside the waveform, the degree to which they are outside the waveform, the concentration status of the data points, and the percentage of data outliers. In general, on the same axis, there are more data outliers in the figures for the 2.5 blade setting than in the figures for the 3 blade setting and in the figures for the 2 blade setting. And it seems that on the x-axis and the y-axis, apart from the ranges of the acceleration magnitude, with the 2 blade setting, the data points are more concentrated than those with the 3 blade setting. Together with the previous observations, these have paved the way for further processing to obtain the effective information and constructing the judgment rules based thereon. Finally, we come to the conclusion and future works. The results of this study facilitates future data-driven analysis and prediction. For example, to justify what rules are effective to judge the malfunction situations of a wind turbine based on the observed differences. And the success of these works can be meaningful, since they will indicate a way to design an algorithm and then an automatic mechanism to monitor each running wind turbine in real time and detect the possible failure that could happen. And this will be a cost-effective solution. For the future work, we show a trial work to resample the source data and redo the local regression method. And the result, one of the results is like like the right figure. So it's more easier in this way to observe the features in each data set. And it's also possible, of course, to resample the waveform after the local regression method is used. We hope the future works like this are effective to support the works such as establishing the judgment rules to differentiate and predict the health status of blades of wind turbine. And for sure, this study has some certain assumptions. The first assumption is that doing things in transform domain is better than doing things in time domain. The second assumption is that we assume that before the situation is getting worse, the observed cases, which means the 2.5 blade and 2 blade cases, will happen in front of those more unhealthy cases. This assumption is reasonable. And we assume that the basic mean bar transform in statistics is effective, and the frame size used for our resampling job is effective too. And that's all I have to say about the topic. Thank you so much for the listening.